Welcome to Free Learning Academy. Let's simplify preemptive and non-preemptive scheduling. Imagine you're watching a video and suddenly an urgent notification pops up on your phone. Instantly, the video pauses, the notification takes over your screen, and after a moment, everything goes back to normal. It feels smooth, almost effortless. But behind that smooth experience lies a very important decision the operating system is constantly making. Should it interrupt a running task or let it finish? That single decision is what brings us to the idea of preemptive and non preemptive scheduling. At this point, you already know that the CPU cannot truly run multiple processes at the exact same time, especially in a single core system. The operating system quickly switches between processes, giving each one a small slice of time. This switching is what creates the illusion of multitasking, something we briefly connected with process execution earlier. Now, the real question is, when should the OS take the CPU away from a running process and give it to another one? In non-preemptive scheduling, the answer is simple. Once a process gets the CPU, it keeps it until it finishes its execution or voluntarily gives it up. The operating system does not interrupt it forcefully, it waits patiently. Think of it like a person using a microphone in a meeting. Once they start speaking, no one interrupts them. They continue until they are done. Only then does the next person get a chance. Let's take a simple example. Suppose three processes arrive in this order. Process A takes 5 seconds, process B takes 2 seconds, and process C takes 1 second. In non preemptive scheduling, process A starts first and runs for the full 5 seconds. Even though B and C are shorter and could finish quickly, they have to wait. Only after A is completely done does B get the CPU, followed by C. This approach is easy to understand and simple to implement. There is less overhead because the OS does not have to constantly interrupt processes. There are fewer context switches, so the system can be efficient in terms of resource usage. But there is a downside. Imagine if process A is very long, maybe 20 seconds. All other processes, even very small ones, will be stuck waiting. This leads to poor response time. If a user clicks something, they may feel the system is slow or even frozen. Now let's shift to preemptive scheduling. Here, the operating system has more control. It can interrupt a running process and take the CPU away, even if that process is not finished. Going back to the meeting example, this is like a moderator who can stop a speaker midway and give someone else a chance. It may sound strict, but it keeps things fair and responsive. Let's revisit the same processes. A takes 5 seconds, B takes 2 seconds, and C takes 1 second. Suppose A starts first. After a short time slice, say 1 second, the OS interrupts A and gives the CPU to B if needed. Then it may switch to C. So instead of waiting long, smaller processes get a chance quickly. A very practical example is your smartphone. When you are scrolling social media and a call comes in, the system immediately interrupts the current app and shows the call screen. That is preemptive scheduling in action. The OS decides that the new task is more important or needs immediate attention. This approach improves responsiveness. Short tasks get completed faster. Users feel the system is quick and interactive. This is why most modern operating systems use preemptive scheduling. But again, there's a trade off. Every time the OS interrupts a process, it has to perform something called a context switch. It saves the state of the current process and loads the state of another. This takes time and resources. If done too frequently, it can reduce overall efficiency. Now let's compare both in a more intuitive way. In non-preemptive scheduling, once a process starts running, it is safe from interruption. This makes it predictable. It is often used in systems where tasks are simple and timing is not critical. For example, early batch processing systems worked this way. Jobs were executed one by one without interruption. In preemptive scheduling, the OS actively manages CPU allocation. It can stop a process anytime. This makes it more flexible and suitable for interactive systems like desktops, mobile devices, and real time environments. Let's take another example to make this clearer. Imagine you are at a billing counter in a store. In a non preemptive system, If one customer has a huge cart full of items, they will be billed completely before the next customer gets a chance. Even if someone behind has only one item, they must wait. In a preemptive system, the cashier might say, let me quickly bill this one item first and then continue with the bigger order. This improves fairness and reduces waiting time for others. Now, think about situations where each approach is useful. Non-preemptive scheduling works well when tasks are short or when interruptions are costly or risky. For example, in some embedded systems where operations must not be disturbed once started. Preemptive scheduling is ideal when the system must respond quickly to events. For example, in a time-sharing system where multiple users are interacting at the same time, or in real-time systems where delays can cause problems. Another important difference is control. In non-preemptive scheduling, processes themselves decide when to release the CPU. In preemptive scheduling, the operating system is in control and makes that decision. Also, in non-preemptive scheduling, starvation is less likely for long processes because once they start, they finish. In preemptive systems, if not designed carefully, some processes might get repeatedly interrupted and delayed. This is something we will explore later when we discuss scheduling problems like starvation and aging. So, if you step back and look at the bigger picture, the difference comes down to one simple question: who controls the CPU, the process, or the operating system? In non-preemptive scheduling, the process holds control until it is done. In preemptive scheduling, the OS takes control and decides how CPU time is shared. And this decision shapes the entire behavior of a system. Whether it feels fast or slow, responsive or sluggish, fair or unfair, all of that depends on how scheduling is handled. As we move forward into specific algorithms like first come, first serve, shortest job first, and round robin, you will notice that some are naturally non preemptive, while others are designed to be preemptive. Understanding this difference now will make those algorithms much easier to grasp because at the core, they are all just different ways of answering the same question: who gets the CPU and for how long? That is it for this video. See you in the next one.